This is lecture 15, part 1. In last lecture, we have discussed that Routh-Hurwitz criteria and we have solved some problems. Two special cases we have noticed. One is that full row of the Routh table may become 0. So in that case, we need to form that auxiliary equation, and the other case is the element in the first column may become 0. So in that case, we need to follow that epsilon method. So today, we will first one example on Routh-Hurwitz criterion. So that example is, so find the number of poles in the left half plane, in the right half plane, and on the imaginary axis. So that polynomial which is given, this polynomial is the characteristic polynomial. So it is given as s to the power 8, 3 to the power 7, 10 s to the power 6, 24 s to the power 5, then 48 s to the power 4, 96 s to the power 3, 128 square, then 192 s plus 128. So if we look at the necessary conditions, then two necessary conditions were there. One is all the coefficients should be with same sign. So here you can see that the coefficients are with same sign. Here 1, 3, 10, 24 like this, all are with same sign. And the second one is no coefficient is missing in this polynomial. So being a stable polynomial, two necessary conditions are satisfied. So now we will be applying Routh-Hurwitz criteria to see whether there is any sign change in the first column or not, because we know that the number of sign changes indicates the number of poles on the right half of that S plane. So let us form that Routh table. So first we need to write that level, that is s to the power 8, s to the power 7, s to the power 6, s to the power 5, 4, 3, 2, 1 and 0. So here the first one is, that is 1, here 1, then 10. So we can write that this is 1, this is 10, then 48, 128, 128. Then in the next row you have 3, 24, 96, 192. So interestingly, one thing you can notice here, whenever you form Routh table, you can also take common and can simplify it. So here if you take common, so that is divided by 3, so that would be 1, and here you have that 8, then here you have 32, and here you have 64. Just I have taken 3 common. So when you will be forming that Routh table, avoid division by negative number. So you can take common only that positive number, because if you take -1, so then it may change that result. So now we proceed, because we have seen that the product would be like this one divided by this. So the first one is, that is 10, this one, minus 8, that is 2 divided by 1, that is equal to 2. So the second one is 48, because the next one is that 48 minus 32, so 16 divided by 1, so that is 16. So here you can notice as we have taken common, so then those numbers become small and it helps us to form that Routh table easily. But you can also go with the original number, so then in that case only the number should be the large number, big number, and but the results remain same. And here in the third case, that is 128, here 128 minus 64, so that is 64, and the second case that would be 128, because here you can see that is 128 and minus 0 divided by 1, 128, and here we can again take that common 2, so that is you have here 1 and 8, then 32, just we are taking 2 common, so that is 64. So now the interesting thing you can notice here, this row and this row, they are identical. That means the next row it would be the all elements would be equal to 0. So then we have seen in last lecture, that means whenever all the elements in a row become 0, so then we need to form that auxiliary polynomial. So for forming auxiliary polynomial, what we need to do? We need to go one step above and form that auxiliary polynomial, that is AS. So here the auxiliary polynomial, that is AS, and you can see here that is s to the power 6. So this is s to the power 6, this one, then 8 s to the power 4, because that would be one even polynomial we have already discussed, and then 32 square plus 64. So this is that auxiliary polynomial, and then we need to take the derivative of that auxiliary polynomial with s. So if we take that one, it would be 6 s to the power 5, then 32 cube and plus this one 64s. So then we have three coefficients. Here you can see that 6, 32 and 64. And you can see here that to the power 5, s to the power 3 and s to the power 1. So in this case, what we need to do, we need to replace those coefficients 0 by that coefficient, that is 6, and then 32, this one, and then 64. So now you can see here that we can take 2 common. So if we take 2 common here, so it would be 3, then 16, and here we have 32. And we know that after replacing those coefficients from the auxiliary polynomial, then we can proceed. And here the next term would be, so 3 into 8, 24, minus 16 into 1, that is minus 16, so 8, and divided by 3, so we have 8 by 3. Similarly, here we can see that 3 into 32 minus 32 into 1 divided by 3, so you have 64 by 3, and you have 64. So now if you multiply, that means if you take 3 by 8 common here, so then you have this one equal to 1 multiplying with 3 by 8, and this term would be equal to 8, and this term would be equal to 24. So then if we proceed, what we get, so 1 into 16 minus 8 into 3, so 16 minus 24, that is minus 8 divided by 1. So that is, you have minus 8 here. Similarly, 1 into 32 minus 24 into 3, so that is minus 40. So now if you just take 8 common here, so then you have minus 1, and here you have minus 5. So as I have pointed out, whenever negative number should be there, should take only positive number common. So here I have taken 8, but if you take minus 8, that result may be different. And here now if we proceed with this particular minus 1 and minus 5, so then this one would be minus 1 into 8, that is minus 8, then minus minus plus, so plus 5, so that is minus 3 divided by minus 1, so then we have 3. Similarly, in this case we have 24. Again, if we take 3 common, so here we have 1, and here we have 8. So then the next one would be minus 5, so minus 5 and plus 8, that is 3, so we have 3, and here we have 8. So this is that Routh table, and again I am pointing out that you may avoid taking those commons. You may go with that original number. So in that case only the number would be large, nothing else, the results remain same, or you can take that positive number common that I have taken here. So now for testing stability we need to look into the first column. So here the first column, you can see here the first column is this one, the first column is this. But if we go with that standard method, we would not get that correct result. The reason is here you can see that all elements in a row become 0. So we have taken that auxiliary polynomial, and from here it is clear that from this particular row to bottom, so this particular part of that Routh table indicates how many poles and zeros are in the S plane of this particular even polynomial. And in last lecture we have discussed that even polynomial has roots symmetric with respect to the origin. So then just look at the first column, what happens here. So first one is 1, this is 1, 3, 1, but here there is 1 minus 1, 1, 3, 8. So we can see here that there is a change, plus 1 to minus 1, and again minus 1 to plus 1. So here you have a change, sign change, and again you have a sign change. So two sign changes are there. So whenever two sign changes are there, then it is clear that for this particular auxiliary polynomial, even polynomial, two roots of the even polynomial, that is that auxiliary polynomial, in the right half plane. So two roots of the even polynomial in the right half plane. Since two roots are there, and we know that in case of even polynomial the roots are symmetric with respect to origin. So obviously two roots, to maintain the symmetry with respect to origin, so two roots of the even polynomial in the left half plane. So because of due to symmetry with respect to origin, so then we can see here the degree of the even polynomial is 6. So it has 6 roots. So we already get that 2 roots are in right half plane and 2 roots are in left half plane because of that symmetry. So the other 2 roots should be on the imaginary axis. So 2 roots on the imaginary axis. So this particular analysis is only on the even polynomial. That means from this particular point to bottom. Now we can see here this particular polynomial is with degree 8. So that means there are 8 number of roots, and this particular part is showing the location of the other 2 roots. So here you can see that there is no change of sign. So this is 1, this is 1, and this is 1. So there is no change of sign. So that means the other two roots, so here if you look at the other two roots also will be in the left half of the S plane. So that means for that even polynomial, two roots are on right half plane and two roots on left half plane, so plus two roots in left half plane. So these roots are, we are getting the locations from this part of the Routh table. So finally what happens? Finally we can see that four roots, we can see that four roots, four in left half plane from here, two in right half plane and two on imaginary axis. So your problem was to find out the location of the roots, in the left half plane, right half plane and on the imaginary axis. And here in this particular example we have faced that particular problem. That means one row becomes completely zero. So in that case we have taken that auxiliary polynomial and then we have taken derivative and replaced the zero by those coefficients and then we proceed. And in this particular example I have shown that we can take also that common, the positive numbers, and then we can proceed, so that forming a Routh table becomes easy. And then we have used that particular property of even polynomial, that means the roots are symmetric with respect to origin, and then we get this result. So Routh-Hurwitz criteria that we have discussed in last class, that means this is a method for finding roots of a polynomial in S domain, and it has two limitations. One limitation is it is only applicable to the polynomial with constant coefficients, and second one is the stability boundary is always treated as imaginary axis. That means you need to find whether roots are in left half or right half plane. So if there is no change of signs in the first column of Routh table, then all roots are in the left half of plane, and number of sign changes indicates that how many roots are in right half of plane. But there are two special cases. In one case, that all elements in a row become zero. So in that case we need to take that auxiliary equation and we need to apply the concept of that even polynomial. And the other case, if the first element of a row becomes zero, so then we need to follow that epsilon method, but sometimes that epsilon method may fail. So now we are going to discuss the time domain analysis. So in this particular topic, that is the time domain analysis, so in this particular topic we will be discussing the time response of first order systems and second order systems, and we will be just discussing some terminologies, or we will see how to characterize the time response of a first order system and how to characterize the time response of second order systems. And so let us start with the first order system. So first order system. So here you have a system with the transfer function, say S, A by S plus A, and you have applied one input, and we are interested in to find what would be the output. So this is that system, and in this particular analysis we will be considering three input signals, that is three standard signals. One is that impulse, then step and ramp. We have already discussed those signals, and I think you have studied in your signals and networks course in detail. So now let us see what would be your output whenever input is unit step. So suppose input is unit step. So in that case, that output ys is equal to that a divided by s plus a into us. So in this case, that us equal to 1 by s, so that would be the output. And what is yt? So yt is that Laplace inverse of ys. So then you would have that Laplace inverse of 1 by s by 1 by s plus a. So then you get that 1 minus e to the power minus at. So that means whenever you apply a step input, unit step input, so then you have this response. So now let us draw this response. So this is that time axis, and here you have that yt. So we have applied that step input, unit step input, so that is that value 1, and you can see here that means when t tends to infinity, so this term would be equal to 0, and so that output will reach at the value 1. So it is close to that 1, but when t tends to infinity it reaches at 1. So then the response this is the typical first order response, and here you can see few things, that is when t equal to 0 it has some slope, and we can also analyze this particular response. Here you can see this yt equal to 1 minus e to the power minus at. So when, so this is that 0 0, when t equal to 1 by a. So you can see here, if you just replace t equal to 1 by a, then yt is equal to 1 minus e to the power minus 1. So that is 0.632. So that means at t equal to 1 by a, so that is, if you take the perpendicular one, so this one would be equal to that 0.632, and this particular value is 1 by a. So now if we take that this point is 2 by a, and suppose this point is 3 by a, this point is 4 by a, then here if we take the derivative of this particular expression with respect to time t, so what we get? We get that dyt by dt when t tends to 0, so that one is a e to the power minus at, that is a e to the power minus at, and we are finding it at t tending to 0, that is equal to a. So from here it is clear that this particular slope equal to a. So now we can give some definition to characterize the response of a first order system. That is, the first one is the time constant. So basically the first order time response is characterized in terms of the time constant. It is the time it takes for the step response, and here you have seen that we have applied unit step response, for step response to rise to 63.2%. So here you can see that this value is 0.632, so 63.2% of its final value. So that means here the final value is 1, so the time takes, so this is the time, here you can see this is the time 1 by a, so this time takes to reach 63.2% of that final value. So this particular time 1 by a is called the time constant. So here we can see the time constant equal to that 1 by a in this particular case, and the slope, initial slope, is equal to a, so then we can write that this is 1 by time constant. And in this particular time response we can also define some other times, that is that rise time and settling time. So here you can see the rise time is defined like this. Rise time, that is the time required to go from 0.1 to 0.9 or 10% to 90% of its final value. So here you can see that the final value that we have, that is 1, because we have applied that unit step. So now that 0.1%, 0.1% means here, so suppose this is 0.1%, 0.1, and suppose this is that 90% here, so this is suppose that 90%. So now according to that definition, the time taken to reach that 0.1 to 0.9 of the final value. So this is actually the time the system takes to reach up to 0.9 from 0.1 of its final value, as the final value is 1. So this is the time, and we indicate that time is equal to, say, TR. That is that rise time. So here this is that rise time, and we can easily calculate what would be the rise time in this case, because we know that yt equal to 1 minus e to the power minus at, and here if we say that this time is equal to t1, so we can say that this is t1 and this one would be 0.1. Similarly, the other equations we can have, that is 0.9. So that means we can find this time, and if we say that this is t2, so then we can write that 1 minus e to the power minus at2 equal to 0.9. So then from here, just by taking logarithm, so we can find that TR, it would be, say, T2 minus T1, and that would be 2A ln 3, which is, that is 2.2 by A. So that means here you can see that the time, this is 1 by A and this is 2 by A, so it takes a little bit more time than the double of that time constant, and this is called that rise time. So in case of first order system, the rise time is defined as, the time taken to go from 0.1% to 10% to 90% of its final value, and here we have calculated that it is nearly 2.2 by A, and 1 by A, this is time constant. So if we say that this is equal to T, if we say that this is equal to T, this value equal to T, that is 1 by A, so basically it would be equal to 2.2 times of the time constant T. So now we are going to define another term related to that time response of first order system, that is settling time. So we say that the settling time is denoted by Ts. So by definition, settling time is the time for the response to reach and stay within 2% of its final value. So we have applied here unit step input, and we can see the final value is equal to 1, and then the settling time is actually the time required to reach and stay. So here if we look at here, so it is almost here where it reaches within 2% of the final value, and it stays inside that range. So it is almost, we can see that is that 4 times of the time constant, and here we can just mention that this is actually the time, and this time is Ts. that is that settling time. That is that settling time, and we can easily calculate it because we know that yt equal to, here we can see that yt equal to 1 minus e to the power minus at, and this yt would be equal to 0.98 if we take 2%. In some cases we take the definition considering 5% as well. That means if your system is very slow, so in that case we take say 5%. And so here we can write that 0.98, that is that yt. So that would be within 2% of its final value, that is 1 minus e to the power minus at. So now if you take logarithm, so then you will get that this t, so that is actually equal to minus 1 by a ln 0.02, and it would be coming nearly 4 by a, so that is 4 into t. So this is your settling time. So in case of first order time response, we have seen that the time response of the system is characterized in terms of the time constant, and here we have seen the time constant is 1 by a. We can see here the time constant is 1 by a, that is defined by t, and by definition the time constant is the time required to reach 63.2% of the final value. And from here also we have defined that rise time and settling time, and we need to remember those things. That means rise time in case of first order systems, it is nearly 2.2 times of the time constant, and the settling time, it is nearly 4 times of that time constant. And the initial slope that you can see, that is the 1 by time constant, that is 1 by t, or it is a. And also it is clear from this particular transfer function that this time constant, so if you write it in this form, that is a divided by, if you take common a here, so that is a into s plus 1, so that is 1 by a into s plus 1. So this particular a is actually the pole of that system, first order system. You can see here, this is actually the pole of that system. So pole of that system is related to the time constant, because reciprocal of that pole location is the time constant, and the time response of a first order system is characterized in terms of the time constant. So now we will see what happens. That means if we apply the different inputs like ramp, or if we apply impulse. So now we are interested in to see, that means what is that unit impulse response. Unit impulse response. So let us take that GS. So now we are taking that transfer function in that form st plus 1. So just now we have seen, that means we can write it in this form. So this form particularly, that is 1 by a, that is the t. So we have written in this particular form GS equal to 1 by st plus 1. So now it is unit impulse, and if you take Laplace transform of the unit impulse, it would be 1. So that ys, so the ys equal to 1 by st plus 1, and then from here you can have that yt equal to 1 by t e to the power minus t by t, and this is t greater equal to 0. So this is that unit impulse, and here if we draw the response, this is that time, and here you have that yt. So when t equal to 0, here, so that means it starts from that 1 by t, and if this is the time constant, that is 2t, 3t, 4t. So basically that the final value is 0, and it takes 40 times, t is the time constant, to reach within 2% of its final value. And this is that 0, 0. So this is the typical response, unit impulse response, and this is that expression. We get it just by taking inverse Laplace transform. So now we are interested to see what would be the unit ramp response, ramp function. So unit ramp response. So here the ys, and as you know that ramp input is t. So if we take the Laplace transform of that, that would be 1 by s square. So ys would be equal to st plus 1 into 1 by s square, and then we can write it in fractional form, t by s plus t square by st plus 1. So yt equal to that Laplace inverse of ys, and we will get that this is t minus capital T here plus t into e to the power minus t by t, and here that is t greater equal to 0. So here we can see that what is y infinity, that means when t tending to infinity. So basically this term would be equal to 0, and we will get that would be t minus capital T. So what is error? Error at t tends to infinity, because we have applied a ramp input. So ramp input means this is time, and this is that input, say RT. That means this signal we have applied, and this slope equal to 1, because we have applied that unit ramp. So then at error at t tending to infinity, that is t minus uh, t minus small t minus capital T, and so just I need to start it. So here we are discussing that response, that unit impulse we have done, and I think because of some technical problem uh, we need to repeat it again. That is that unit impulse unit impulse response. I am repeating it again because that portion is not saved here. So that is ys that we have, that is st plus 1 into 1 by a square. So I am just writing it because just now we have discussed it. T square is t plus 1, and here we get that yt, the Laplace inverse of ys, and that we get that is t minus t plus t e to the power minus t by t, t greater or equal to 0, and that y infinity equal to that t minus capital T, and here that error at t tends to infinity, what we get. So here we have shown that this is that input we have given with slope 1, that is that input we have applied, that is t, and this is that y infinity equal to t minus t. So that error is equal to at t equal to t tending to infinity, this is equal to say t minus t plus t, that equal to t. So that means if we just plot that response, what we get. So this is t and this is that yt, and we have applied that input. So this is that input, the slope here, this is t. Suppose this is that time constant, and here we have another slope, and we can see the response. The response is like this. And here when t tending to infinity, so that means this particular difference is t, as well as if you take that perpendicular difference, that means if you take any point here, this distance also would be equal to t. The reason here you can see the slope here 1 and here also the slope 1, and t is that time constant, and we can see here that error when t tending to infinity, the error is t. So that means it is interesting to note that whenever we apply step input, then we have this response, and whenever we apply that unit impulse, then we have this response, and whenever we apply unit so this is unit ramp, then we have this response. So now if we write those expressions here, that means unit impulse, so then that is yt equal to 1 by t e to the power minus t by t. We have seen it here, that unit impulse, this one, then that unit step we have that yt equal to 1 minus e to the power minus t by t, and unit ramp, just now we have shown that unit ramp is this one, so that means yt equal to t minus capital T plus t into to the power minus t by t, and all of them is valid when t greater or equal to 0. So one interesting thing we can see here, that if we take the derivative of this ramp response, we will get that step response. And again, if we take derivative of unit step response, we will get that unit impulse response. Because this relationship holds, as you know, that the ramp in signal, if you take the derivative of the ramp signal, you will get that step, and if you take the derivative of step, you will get that impulse. So the same relationship is also valid here. That means it also holds here whenever you take that output response. And what we have discussed today in this particular part, so we have solved one problem on Routh-Hurwitz criteria, and in this particular problem we have seen that same condition, the same situation appears, that is all the elements in that row become 0, and then we have taken that auxiliary polynomial and applied the property of even polynomials. That means all roots are symmetric with respect to origin. And then we have started time domain analysis. We have discussed what is the response of a first order system whenever we apply unit step, unit ramp, and unit impulse. And we have characterized that response, particularly in case of step input, and also the same characterization can be done in case of ramp as well as in case of impulse response. And we have drawn those responses here, and T is the time constant, and in case of first order system, to characterize the time response, we use that time constant T. And here we find one